In this talk, I will provide a quick summary of lessons from over a decade of research on the restoration of boreal peatland affected by in-situ oil and gas activities in Alberta, Canada. On the left is a map of Alberta's peatland. The darker the color, the higher the percent cover in that area. As you can tell, most peatlands are found in the northern boreal regions, which coincide with the oil sands deposit. The majority of Alberta's oil deposits are too deep for direct mining. Instead, it can be accessed only through in-situ extraction process, such as the SAGD technique. This aerial photo shows a typical in-situ oil and gas facility with many well pads connected by linear features to a central processing facility. Collectively, these in-situ footprints fragment the landscape and can greatly affect vegetation, hydrology, soil, and carbon dynamics, and leading to the loss of valuable functions of boreal peatland. There are two general approaches to reclaim in-situ features in peatland. The first is to remove all the introduced mineral fill and expose the buried peat to create a saturated peat substrate that is hydrologically connected to the surrounding areas. The next steps are basically an adaptation of the moss layer transfer technique, MLTT, developed in eastern Canada for the restoration of cutover peatland. Basically, the top 5 to 10 centimeter of living moss fragments, along with seeds, roots, and rhizomes, are collected from nearby cut lines and spread as a thin layer on top of the peat. This approach worked quite well in our field trial. 6 years after revegetation, peatland species reached 71%, and bryophyte covers almost half of the reclaimed site. Almost all the vegetation you see in this photo came with the original donor material and through natural ingress from nearby sources after restoration. Creating the right surface elevation and moisture condition and the transfer of moss donor are critical to the overall success. The second approach was developed based on the fact that many of Alberta's peatlands developed through a process called polludification, where the mineral soil became saturated as water table rose when the climate became cool and moist. Over time, mosses started to encroach and grow, modifying the environment and leading to the eventual accumulation of peat. In this approach, some mineral fill is removed to create a saturated substrate at level with the surrounding peatland. Revegetation can be done through the transplant of cuttings and seedlings, natural regeneration, or through the moss layer transfer. Despite the scientific basis for this approach, the actual initiation of vegetation on mineral substrate varies greatly depending on the moisture and chemistry of the substrate and connectivity with the surrounding areas. Natural ingress of mosses do occur, but is very slow. Instead, transfer of fem moss donors can greatly accelerate the process and lead to the best overall vegetation recovery. In an ongoing study, we surveyed 11 reclaimed well sites and 5 reference peatlands. Although all the reclaimed sites are still different from the natural peatlands, sites that received moss donor transfer are in general more similar to natural reference than those that were reclaimed by planting or left to natural regeneration after the partial removal of mineral fill. These preliminary results show that either peat or mineral substrate can support the development of peatland vegetation, but the chemistry and moisture conditions of the final substrates are critical. Revegetation through MLTT is crucial to accelerate recovery and to prevent encroachment of undesirable species. It is also critical for bryophyte establishment, as natural ingress of mosses is very slow. I've only discussed in-situ footprints built with borrowed mineral fill material in peatland. There are other types of disturbances that need our attention, such as seismic lines and winter access roads that are not recovering as expected. So there is still a lot of work left. We only have learnings from a few sites that were systematically studied. We need more trials and longer-term monitoring to reduce uncertainty and increase resilience of reclaimed systems. We need to look beyond the vegetation and incorporate ecosystem functions such as greenhouse gas balance, nutrient cycling, and wildlife habitat in reclamation planning and assessment. We need to develop effective reclamation techniques to create the suitable soil and hydrologic conditions for the successful establishment of peatland vegetation. Ultimately, we need more properly trained professionals to carry out the work in the field. Thank you.